Hello, Dr. Smith. Before I begin my presentation, I want to quickly thank you for teaching regression analysis this semester. If there were to be one thing to point out that I enjoy learning, I would definitely say it was learning to visualize data points. And now I will begin my presentation. My presentation is titled The KMNIST Image Classification Model Selection. So the objective of this project is to answer the following two questions. How do we improve each machine learning model to its maximum capability? And which machine learning model is best for KMNIST image classification? To briefly introduce myself, I studied computer science for my bachelor's degree with a statistics minor. I am pursuing PhD in big data analytics, and my research interest is in computer vision, specifically image processing and dimensionality reduction. I find computer vision to be fascinating because it performs the same tasks, classifying tasks that our eyes and brain do. And vision is a pretty important sense that we really rely on. So I find computer vision to be a quite significant research area. The KMNIST dataset, it is short for the Kuzushiji Modified National Institute of Standards and Technology Dataset. And this dataset consists of images depicting handwritten Japanese characters. There are a total of 70,000 grayscale images, in which 60,000 of them are used for training, and 10,000 of them are going to be used for testing. Each image is made out of 28 by 28 pixels, resulting in a total of 784 variables per observation. And there will be 10 different Japanese characters that we will be classifying for. So here is the example of the characters. There's different ways to write in Japanese, but the most common writing system is called hiragana. So basically, class 0 represents O, class 1 is ki, 2 is su, 3 is tsu, 4 is na, 5 is ha, in which case that's not the hiragana character, so it looks different. And 6 is ma, um, 7 is mi, 8 is ya, and 9 is re. Uh, so yeah, because there's different ways to write, it will be interesting to see different types of characters and how our models will perform. To go deeper into each examples, so I printed out 10 examples each for class 1, for example. Um, yeah, some of them do look different. Oh, class 0, they look consistent. Class 1, there are similarities and differences. Class 2, and so on. So I'll just briefly go over all 10 examples. And I think class 5 is one of the examples where there's like some of them, a few of them are hiragana, but the rest are not. Ma looks consistent, mi looks consistent. Ya, there may be a little bit of variations, and re. So before we train our model, I went through some pre-processing. Firstly, variable selection. The 784 pixel variables are not independent. And this is because the neighboring pixels create spatial structure. So this classification task will be different from the regression tasks that we did during class, where correlated variables are unwanted. We actually want all the pixels, so all the pixels will be taken into consideration. Next, I looked at outliers. Similarly, we can't use scatter plots or the summary function that we did in R to use p-values to detect outliers or anomaly because the neighboring pixels create spatial structure. Instead, I took a look at some of the images that could be outliers, such as images with missing values, images with high or low variance, and images with corrupted image files. So here are the top 10 images with the highest variances. In my eyes, they still look like Japanese characters, so they will be kept. Similarly, here are the top 10 images with the lowest variance. In this case, they also look like legitimate Japanese characters, so they will be kept. In my project, I'll be testing two different machine learning models. The first is the K-nearest neighbor model. It's a simpler model. And the second one is a convolutional neural network. This is a little bit more complicated model. So, few ways to improve KNN. Some of the things I applied is normalization, which standards and scales data to prevent specific features from dominating. Because KNN uses a distance metrics to determine its nearest neighboring image and class. That's how KNN is going to classify. So normalization is important and it will reduce computation time and improve convergence and stability. I will also be using class cross-validation to reduce overfitting. So here we have two graphs. Firstly, I'll be talking about the graph on the left. On the y-axis, we have the mean cross-validation accuracy. For this graph, I'm using a cross-validation of 5 folds. And on the x-axis, we have the k-value from 1, 3, 5, 7, and 9. I also have three different distance metrics labeled as blue for Euclidean. We can see that on the middle, orange for Manhattan on the bottom, and green for cosine. Two things we can note for this graph is that as k increases, the overall mean cross-validation accuracy decreases. So there was no need to try higher k values. And for the distance metrics, we can clearly see that the cosine distance metric performed the best. So using this strategy, I was able to find out that the best model will have the hyperparameters of k equal to 1 and distance metric of cosine. The only concern I had with this is that the cross-validation suggested a k value of 1, which I'll discuss about shortly in the next slide. And so to see if this is enough cross-validation, I did try another one with 10 folds of cross-validation. However, similarly, we can see that it gives us the same result of cosine and k equal to 1 being the best parameter. Here, I moved on. Again, I'll be discussing on the next slide. So why am I concerned about K1? K equals to 1 is usually avoided because it's known for overfitting. This is because K equals to 1 means that each image will be classified based on the first nearest neighbor. So I increase the cross-validation folds. What happens is that firstly it's going to increase computational cost and decrease validation size. So it can't overfit, but the tenfold cross-validation is also considered standard practice in machine learning. And it's not a huge number of folds, so it won't overfit, which is why I chose 10. Moving on, we have the two matrices. Again, we'll look at the left one first. So these are the confusion matrices visualized using the heat map function. The left matrix is generated by using a k equal to 1. Firstly, the k equal to 1 model had an overall test accuracy of 93.64%. Some things we can note is that the model misclassified a couple of examples such as images with class 2. There had a tendency to misclassify as class 3, and images of class 1 were, some of them were misclassified as class 6. I still wanted to try k equals to 3, so on the right is the confusion matrix when k equals to 3. However, the overall test accuracy was still a little bit less than k equals to 1, as the graphs previously suggested. We still have similar problems where they were misclassifying similar examples. Looking at the examples, we can see that the 5 images in the first row are class of 1, but they have been labeled as class of 6. We can also see that their corresponding hiragana characters do look similar, so it does show that how the model could have misclassified. Similarly, on the bottom row, we have images that have an actual class value of 2 misclassified as class 3. Moving on. Now I modeled a convolutional neural network. This is different from KNN because it can learn features, actual features such as edges, shapes, and patterns. While the KNN is sensitive to shifts and rotations, the CNN is more robust. So this will be the design of my CNN. Basically, the CNN has multiple layers that the input goes through, and then it will give us a final output of 10 classes. So the original input, we have the original image, 28 by 28 pixels. We also have this number 64, which represents the batch size. The batch size determines how many samples are passed through the network before updating weights. And so choosing small batch sizes can improve generalization, but it's going to cost more time. So I chose the number 64. Then the input goes through the first convolutional layer. So the image goes through the layer and gives us 32 feature maps that detect edges, curves, and patterns. After that, it goes through a max pool layer, which then reduces the 28 by 28 pixels to 14 by 14. This is also called downsampling. It reduces computation and provides translation invariance. Now then, the downsampled image goes through the second convolutional layer, which gives us 64 more complex patterns, determines more complex patterns. Then it goes through the first fully connected layer, which gives us 128 total features. Now the 128 total features are taken into consideration to give us the final 10 classes based on their feature values. So again, I could be using the same technique I used for KNN. It is called grid search to generate the graph using different hyperparameters. But the CNN is computationally more expensive, so grid search was impractical. So what are alternatives? I could have tried different CNNs manually, but in this case, I used a hyperparameter tuning library called Optuna. So the Optuna library, there's many hyperparameters I can choose from. I chose these 3. LR representing the learning rate, dropout representing the fraction of neurons randomly disabled during training, and this helps us to prevent our overfitting and forces the network to learn more robust features. I also use the num filters hyperparameter, which chooses the number of convolutional filters in the convolutional layers. The hyperparameter importance plot. This plot tells us the percent each hyperparameter affected the validation accuracy score. And pretty much it tells us that the learning rate most influenced our overall validation accuracy score. The parallel coordinate plot. This plot displays validation accuracy scores for each hyperparameter choices. So different validation accuracy scores are colored based on its strength, with the highest one being the darkest and the lowest being the lightest. For our case, we can see that the model with the highest validation accuracy score following the darkest line had a dropout value at this point, a learning rate at this point, and 64 number of filters. Going back to the matrices, confusion matrices. On the left, we have the best performing KNN model, which had the accuracy score of 93.64%. And on the right is a new CNN model. The CNN model had a test accuracy score of 95.21%. Similarly, we can see that it still had a few issues similar to the KNN, along with a little bit more on misclassifying examples that had an actual class of 5 as misclassified as class of 2. I tried another instance of CNN with the same settings, which gave us a slightly lower accuracy score, but it's still higher than the KNN, which was 93.64%. Looking back at the misclassified examples, again, the first row shows us images of class 0 misclassified as class 4. The second row shows us images of class 1 misrepresented as class 6. The third row shows us images represented as class 2, mispredicted as class 3, and the last row being images of class 5 misrepresented as class 2. Again, we can also see that the hiragana characters are somewhat similar, which gives us an understanding of why the model may have mispredicted, because they have similar features as well. Conclusion. Going back to the original questions, how do we improve each machine learning model to its maximum capability? Um, well, the answer is we have to try a range of hyperparameters and also visualize them so that we can identify patterns, such as the accuracy score decreasing as k as we increase the number of k values. So we identify patterns to find the best combination of them. And the second question being which machine learning model is best for KMNIST classification. And our results show that CNNs perform better than KNNs, which is not a surprise. And in the future, it will be interesting to see if I can merge these different models to help boost classification by classifying, yeah, better. Well, this is it for my presentation. Thank you again for teaching us this semester. I hope you have a great winter break. Thank you very much for your time.